Hello, everyone, and good day. Sir Jules here. So it's been a while. So for our today's video, we'll be discussing about an introduction to organic chemistry. On the following sessions, I have decided to make a series about organic chemistry to discuss this whole topic about this specific field of chemistry. Now, to start with, I have here an introduction to organic chemistry. So, to shortly start our session, we have different fields of science. We have physics, we have biology, chemistry, biochemistry, analytical chemistry. So, what really is organic chemistry all about? So, what are its components, or what other parts of the field of chemistry falls under the specific study of organic chemistry? So that will be the scope of our discussion for today. But before that, let's have first our learning outcomes. So this our goals that we want to meet at the end of the session. So at the end of this lesson, the students will be able to first discuss the origins of organic chemistry. Second, explain why the carbon compounds are more numerous and more stable than the inorganic compounds of other elements. Third, differentiate organic compounds from inorganic compounds, as these two specific fields of chemistry are the one we always compare from each other mostly. So where do we draw the boundaries between organic chemistry, and when will it be considered it's already part of inorganic chemistry? Now, to start with, organic chemistry, by its nature, is just basically this the branch of chemistry that studies carbon compounds. So, if you'll be taking a look at our periodic table, we have around currently 118 elements, and one of that is the carbon compound, which is the sixth element in the periodic table. Now, as per the definition that we have here, organic chemistry is a branch of chemistry that studies all about carbon compounds. So, what makes carbon compounds a very unique element that we have a separate field of chemistry that only talks about for an entire semester about carbon compounds? Now, we have a lot of things around us are carbon containing compounds, especially us humans. We are carbon organism. All the living organisms are composed of carbons. So where do we draw the line? So if organic chemistry is a study of carbons, so does it also mean that, for example, we have table sugar, which has C6H12O6? Is that part of organic chemistry? How about cyanide, which has um a chemical formula of CN? The carbonates, are they part of organic chemistry too? Now, to start with, in drawing the line between these two, we can only consider, we can set aside hydrogen, cyanides, the carbonates, ammonium cyanate, and others of related nature are as not considered under organic chemistry because they display inorganic properties. So, what are the specific properties of organic chemistry that we can say that's organic chemistry and not inorganic? We'll be discussing that further down the line. But first, let's take a closer look. Let's know more about our friend, the carbon compound. Now, think about um we always have that one guy in our school, our classmate or a friend who is everybody's friend. Everybody wants to be with that person, to get along, to talk with him or take a picture of him. So that's like an everybody's friend. Now, the same thing can also be said about the carbon compound. Carbon, I mean the element carbon. Carbon is everybody's friend. He is the friendliest element in the periodic table. And because he's the most friendly, he wants to share anything that he has. He wants to connect with more people. That's why he can form at around 10 million carbon compounds. Imagine that. Carbon can form over 10 million carbon compounds. And can you please mention anything or any element in the periodic table that can also do the same? There's not. There's not one element that has the similar characteristics or similar structure as a carbon compound does. So carbon is the only element that can make this much 10 million compounds currently, and it's even adding as per the day passes by. So what makes carbon so unique that it can connect with more element, can create this 10 million carbon compounds? So carbon is a cool element, as you can use the term. He's like that friendliest guy in the room. He's a cool element. He's the coolest guy in the periodic table because not only that he can bond with itself and with other elements to form organic molecules, but it can also build itself structures in useful forms. So, what does it really mean? Excuse me. Sorry about that. Um, we have this term we'll use allotrops. So carbon has a number of allotropes that we currently know about. So what is an allotrop? So it's just basically having the same element but used in different structure, in different usage, different functions with different physical appearance. But it's just the same letter C. That's still a carbon atom in it, but it's just arranged differently that it can be used from. This is an amazing idea. Carbon has the softest and the hardest um allotrope that it can possibly make. So just for example, we have the graphite. The graphite that's a solid but it's just a soft material which is used in our pencil for drawing. So that's a soft material, but the same carbon that is present, the same carbon atom that is present in a graphite is also the same carbon that is present in a diamond, which is the hardest material known as for humankind that has around a 10 Mohs scale. So that's the hardest one. So if we'll put it into an analogy, allotropes are just like names. And do you know what is the commonly used name across the world? It's Muhammad. So it's just like having, let's just say my name is Muhammad, and there's another Muhammad in the Middle East or Muhammad in the America. We have all the same name, but we have different structures, different functions, but we're just the same Muhammad. So just like carbon is the same carbon, which is inside a diamond, inside a graphite, inside a lone sodalite or amorphous carbon, but they perform differently, they function differently amongst each other. And you know why? Because carbon is a versatile, it's a flexible element. And these are the following, I'll be discussing further down the line the following characteristics that leads to why carbon can be this flexible, this versatile, and can be useful in a whole lot of range of functions and uses in our daily lives. So why is carbon the friendliest element? So in comparison to inorganic compounds or elements, so first, carbon, it has a tetravalency, or he can form four bonds with no lone pairs. So um, this was discussed in inorganic chemistry, the Lewis electron dot structure. When we talk about lone pairs, that is a pair of electron within that specific element that can't pair with another because it already paired up with itself. However, for carbon, it has around four electrons in its outermost valence shell, and all that four are available for pairing. And if this was discussed with you, always remember elements, the goal of the elements is to be happy. And how can they be happy? We have the so-called the octet rule. An element will only be its happiest and its most stable form if it has eight um, valence electrons in its outermost shell. And carbon being having the four valence electron, he can share all of those four with other elements, which leads to creating of carbon compounds. And An element can be happy because it shares the 4 plus another 4, it becomes 8. They now satisfy the octet rule, so the element, the compound is now happy. So that's just basically it, because it has tetravalency. It can form 4 bonds. That's the maximum an element can ever bond with another element. Now, second characteristic of carbon, it's catenation. So what do you mean by catenation? So catenation is the ability of an element to sustain or to create longer chains of compounds, longer chains of its atoms connecting from one another. Now, if you think about it, it's just like here in the Philippines. The longest bridge in the Philippines is the Sislex Bridge, which is located in Cebu. So carbon is like the Sislex Bridge. It can create that lengthy bridge across the seas while still maintaining to able to support its structural support, meaning it can sustain no matter how long it can get or how long it could possibly make. Carbon will be able to sustain that one. So aside from linear bonds, carbon can also form ring bonds. So that will be another discussion as we go further down the line. But that's one characteristic of carbon that makes it able to create 10 million compounds. It's catenation. It can sustain lengthy structures of connection of different atoms. Now, number three, strong carbon to carbon and carbon to hydrogen bonds. Now, this one, why carbon to carbon is a strong bond? Because basically carbon has 4. If it's connected with another 4, it becomes 8, thus satisfying the octet rule. And that's it. That's a strong bond because once an element or a compound is stable, it wouldn't want to be disturbed because I'm now happy with my life. So why do I want someone to interfere with me and try to destruct those bonds that I have currently, which is the most stable that I have, right? And then we also have the carbon to hydrogen bond. Um, this, just like the carbon to carbon and carbon to hydrogen bond, these are both nonpolar, which means that they have close enough electronegativity values. So which means no, it's like having a tug of war. If one element has a big difference of electronegativity from the other, this stronger element will be trying to pull away all the electrons to its side. So that's a polar um, compound. So they have different, which one is more positive, which one is more negative. But for the case of carbon to carbon and carbon to hydrogen, they have close enough electronegativity values that allows them not to pull a tug of war from each other, but instead a stable harmonious relationship, holding and sharing that same number of electrons amongst each other, if you get the picture. So yeah, that's the reason why. And then number 4, multiple bonding. We have single, double, triple bonds. So that will also be discussed as we go further down the line. But carbon is an element that is capable of creating or making this single, double, or triple bonds within itself. Other elements aren't capable of doing that. Only carbon, if I'm not mistaken. And number 5, ability to form functional groups. If we'll be also be discussing this further in line, but some of the functional groups are the aldehyde, the alcohol, the ketone, the ester, just to mention a few. So those are different functional groups, which is derived mainly from the carbon compound. So when we form it from a different structure and how we arrange them based on their molecular structure, that will create different functional groups that can serve different purpose in our daily functions. Just for example, we have alcohol. If we'll just change a little bit about alcohol, then we can make ester or ketone. Though some of those are being used in our perfumes, so it performs a whole different function just because we arrange a different one. So it forms different functional groups. It is very diverse. It is flexible. It creates different as you name it. And isomerism. So isomers are basically this elements or compounds that have the same um chemical formula but performs this differently and looks differently on a molecular scale. So just for example, let's have butane. Butane, I think if I'm not mistaken, it is bu. That's C4H10. So we have butane, but we also have the isomer isobutane. So how does it happen? It just depends on where do we place the carbon compound within their molecular structure. So it becomes from butane to isobutane. So just one example, think about of the different elements or different compounds a carbon can form, and we just disarrange it to form different isomers, even having the same molecular formula. So it creates diversity, very versatile, very flexible. And last but not least, its biological relevance. As I mentioned earlier, all living organism are organic organism. That's why it's called organism because it contains organic compounds. Just for example, in the human body, the second most abundant element in our body is carbon. Second to oxygen, which is around 60%, and carbon is around 15 or to 20% around that range. All living matter have carbon compounds in it. So that's why it's really relevant. Without carbon, we wouldn't be formed. It can't form the structure that we currently have because only carbon is capable of forming what we currently are as of the moment. Now, in comparison to inorganic elements, how different it could be between organic elements and like, inorganic elements. So first, it can't form long chains with themselves. So it have poor catenation. So let's just say, for example, let's think about cyanide. Cyanide contains carbon, but is not considered as part of organic chemistry. Why? Because cyanide, as a compound with its specific characteristic, it doesn't display the characteristic that organic compounds has. It has poor catenation. It can form longs of cyanide, cyanide, cyanide connected within each other. In comparison to carbon, other carbon compounds, let's just say alkanes. So from butane, propane, hexane, the lines just keeps on getting longer, but it can sustain itself because it has good catenation. Number two, don't support multiple bond types as well. So we have the single bond, double bond, triple bond. Other elements can do that, only carbon. Number three, tend to form ionic or simple covalent compounds. Now, this is very important. Why? Because going back to the rule that elements wants to be stable, accomplishing the octet rule. But the most stable polarity that an element could ever have is non-polar. They don't have sides that they want to side on. For example, this positive, this negative. If this element is more positive, then it would be grabbing along more of its electrons. So it's like having a tug of war. So if we form ionic compounds, for example, sodium chloride, because chlorine has more electronegativity than sodium, then more likely that one electron that sodium has, it will be giving to chlorine. So they're not sharing it, and it's it's not a polar bond, but it's an ionic bond, which has different polarities. Now, that's just to give you an idea. Number four, have more limited bonding patterns. Just for example, carbon compounds can form different carbon bonding patterns. Just disarrange or put the carbon in the middle or in the center or in the side. It would be now a different pattern. But compared to other elements, if you'll be doing that, then I don't think that could also work out for them as well. So that's just the basic difference as to what makes the carbon compound as the uh, Around it can form around 10 million compounds as the friendliest element in the periodic table. Now, just to give you an overview, comparison of organic and inorganic compounds. So just for example, organic compounds include plastics, alcohol, inorganic compounds, for example, table salt, sodium chloride. So the source is living or non-living things, but inorganic, it only can be derived from non-living things. So elements, mostly chance, these are the life-sustaining elements, the chance. And inorganic compounds includes all abundance around 3 to 4 million, and inorganic is only 300s. So the list goes on. So this is just an example, an overview of how we differentiate organic from inorganic compounds. Now, to give you to the next topic of the history of organic chemistry. So it's about debunking the vital force theory. Now, just like any other science, or the process of science itself, before we arrive with the final theory or a conclusion, failures must be met along the way, right? So the same thing can be applied or be said on how organic chemistry came to be as a different field of study of chemistry. Because before, way back then, scientists used to believe in the vital force theory. So what is that theory all about? Vital force theory talks about, because we have mentioned that we have organic compound. These compounds, organic compounds, can only be derived from living things. That's why it's vital force. So just for example, urea. Urea is an organic compound, which is a composition of our urine. So scientists have thought about that, yeah, since it's part of organic compound, urea can be only produced by humans by urinating. But that's not the case. And we have here that guy who discovered it, Friedrich Waller. So he's a German chemist who prepared urea, an organic compound, so that is from the a product of urination, that's part of a urine of a human, and he was able to synthesize that with an inorganic compound, which is ammonium cyanate. So basically, that experiment debunked the whole vital force theory. Urea can also be produced through using inorganic means, not just by urinating from humans. So that's how it all went to be. Yeah, we can do that. We have to debunk this because it's no longer useful. And around in 1858, Cooper and Kekoli described the tetravalence of carbon and the formation of chains of carbon atoms independently. So this is a discovery or reason why carbon can form such enormous number of compounds. So as I mentioned before, it's tetravalency. And because of this discovery, they realized that since carbon can form these numerous numbers of compounds, which is approximately around 10 million compounds, right? And in comparison to inorganic chemistry, they can only form around hundreds of thousands. So that's the limit. So they realized that with this much number, with this specific characteristics, with this formation of compounds, we have to make a separate field of it. Because it will be um, joining together inorganic chemistry and all these organic compounds, the whole thing would just go on and go on. So in order to make a distinct specific field of chemistry to discuss just about these organic compounds that have the specific characteristics and how they form, how they function, how they behave themselves in a molecular structure, then the answer is, for organization purposes, is to create a different field specifically in the study of the organic compounds. So that's how organic chemistry came to be. All right. So I think that's the end of my discussion. So I hope you learned something from my videos. It's been a lengthy um, talks about organic chemistry, but it's going to be fun further down the line as we'll be discussing more about its technicalities, especially naming compounds. That will be a challenging and exciting part. All right, so thank you so much for today, and I'll see you in the next one. Hope you enjoyed the lesson and have learned something. Bye bye.